So you still haven't had enough kinematics? Okay, here's some more. What are they giving us here? A bus initially at rest pulls away from a bus stop with constant acceleration. Okay, so this bus is moving sideways. It's not falling like a rock, so it has an acceleration which is not 9.81. 1.5 meters per second squared. And they said initially at rest, which means the initial velocity was 0. And they're saying it gets to a final velocity of 60 kilometers per hour. I'm writing that like 60 kilometers per 1 hour because that unit's not going to work for us. As soon as we normally prefer to work with our distances in meters and our times in seconds, so this is going to take some manipulation. Now, if you just want to, I'll just tell you this because it's useful to know. If you have kilometers per hour and you divide that number by 3.6, that will give you meters per second. You might just want to put that in the corner of your sheet. It'll save you some time. But pretend for a moment that you don't know that. The way that you would convert this thing is you would say, I know there are 1,000 meters in a kilometer, so I can say there are 1,000 meters in 1 kilometer. And I wrote it this way because I want kilometers on top and kilometers on the bottom to cancel. Now my velocity is in meters per hour, which is sort of an improvement. I also have to fix this time, which is in hours. I know there are 60 minutes in an hour, and I'm going to do this wrong just to show you. 60 minutes in 1 hour. Why is this no good? This is no good because we want our hours to cancel, and they're not going to. They're both in the denominator. So if we do this, we get meter minutes per hour squared, and I have no idea what that means. What we actually want is the hours on top. We want them on top because we want these hours on the bottom to cancel against the hours we're putting. So we're going to say 1 hour is worth 60 minutes. If we do that, hours cancel, hours cancel. Now we have a velocity in meters per minute, and we can do that again and say 1 minute is worth 60 seconds. Minutes cancel, and now we're there. So to get this number, what we're doing is 60 times 1,000 times 1 times 1, don't do those obviously, divided by 1, divided by 1, don't do those either, divided by 60, and divided by 60. So 60 times 1,000 divided by 60 twice. Oop. Minor calculator fumble, but we're going to be okay. I get 16.67 meters per second is our final velocity in good units. Fair enough. And if you do it this way, if you do 60 divided by 3.6, then you got this same answer, and you got it about a minute and a half ago. So good on you. This is a nice shortcut to know. It saves you having to do all this stuff. Okay, so, oops, I meant to have that question covered up. Sorry about that. Please ignore that. So if they want the time required to get to that velocity, we have this great little formula which can get us a time. If we're solving this for time, we'd have to subtract VI from each side. That gives us VF minus VI equals AT, and then we divide both sides by A, and we get VF minus VI over A is T. So final velocity 16.67, initial was 0, acceleration is 1.5, and if we do that, we get 11.11111 seconds. Now, this acceleration had 3 significant digits, this had 3 significant digits, so our answer should have 3 significant digits. That means 11.1 is what we should be saying. Good. The next question is about the same bus. Let's get that up here. Okay, so same bus. We still have our 1.5 meters per second squared for the acceleration. And we had an initial velocity of 0, and we had a final velocity. I haven't even looked at the question yet. I'm just getting this down because I assume we're going to need it. Okay, what distance did they cover? Well, let's give this thing its due. It's a terrific formula, and it's exactly what we want for a situation like this. Our final velocity is 16.6. You know what? I guess that should be 1667 if we're rounding correctly. 16.67 squared equals 0 squared plus 2. Acceleration's 1.5, and we don't know d. So 16.67 squared is 277.88888. That should be enough. 0 squared is 0, forget about that. 2 times 1.5 is 3. And if we want d by itself, right now it's multiplied by 3, so to get rid of that, we divide both sides by 3. We get a displacement of 92.6 meters. If you're tired of using that formula, you could also have used distance equals VIT plus 1/2 AT squared. Initial velocity was 0. We found in the previous problem that the time was, 11.1 seconds? And then here you'd have 1/2, 1.5, and 11.1 squared. If you crunch all that out, that should also give you 92.6 meters. VF squared formula is great, but I'm trying not to massively overuse it. Okay, what are they doing here? This is complicated. 2 baseballs are projected upward. The first ball is 23 meters per second, and it's released 1.5 seconds before the second ball. But they both reach their maximum heights at the exact same time. So, okay, well, there's one ball where we know all the stuff, so let's start with the one where we actually know everything. We have one where we start with an initial velocity of 23. Nearly all baseballs are on Earth, so we know our acceleration is minus 9.81, and that ball is going to go up, and it's going to come down. And they want maximum height. Oh, you know what? Now that I see the question, I don't think we even care about that second ball. They're just saying what's the maximum height of the first ball, so this is going to be a snap. VF squared equals VI squared plus 2AD. Oh no, we don't have VF. Or do we? If this is the point we're interested in, where we're at maximum height, the velocity there is 0. At that point, the ball stops in the air for just an instant and then begins to fall back down. So, if we plug that in, we get 0 squared equals 23 squared plus 2 times minus 9.81 times a d that we don't know yet. 0 squared is 0, 23 squared is 529, minus 19.62d. Take the 19.62d over to the left, it becomes positive. 529. And now if we want d alone, right now it's multiplied by 1962, so to fix that we divide both sides by 1962. And we get d equals 529 divided by 1962 is 26.96 meters. That's our max height, but all this data has 3 significant digits, so we should trim this to 3. 27.0 meters would be our finished answer.